Hi everyone. So this week, as we discussed, we're going to talk about measures of central tendency in data sets. And the reason why we're doing this is because, well, I should say measures of central tendency and spread. Why are we doing this? As we discussed in class last week, the most important issue when we're dealing with data, once we feel confident that it comes from a reputable source and most importantly answers the questions that we need it to answer, that it is representative of the issue that we're trying to examine, and that all kind of caveats have been evaluated and limitations have been addressed, is we need to be able to evaluate data in context, right? Now, in interviews with people, most of us do this intuitively, right? We're able to, we spend our whole lives learning how to interpret the signals that we get from other human beings. So we understand their body position, their tone of voice, their inflection, their facial expression, the words that they use, the connotations of those words. All of those are things that humans, that we are very good at kind of processing and getting to the gist or the sort of bigger picture of what someone is saying. With data, we can do the same process, but it's a little bit more explicit for most of us, right? In fact, it has to be explicit. And so in order to do that, one of the key things that we want to understand is, if I look at a given data point, how does that data point relate to the universe of relevant data around it? Okay, so to do this, we look at two things. We look at measures of central tendency and we look at measures of spread. And what that does is it actually relates to visualization. This is partly a visual feature, is it gives us what I like to describe as the shape of the data. What is the shape of the data and what does that tell us? Now, why does the shape of the data matter? Well, as you'll read and as we mentioned, there are different ways to measure central tendency, right? Or what we might think of as the average or typical value in a given data set. So there is the arithmetic mean, which again is the mean or the average, right? That most of us are familiar with, right? We have a number of data points, we add them all up, we divide by the number that we have, and then we have the average. The average is often a fraction or a decimal, and most of us sort of understand that when we're evaluating that average, it doesn't, it's like saying, sort of the average American family has 2.5 children, which I don't even think is true anymore, but obviously we understand that it has sort of real world limitations. The median, by contrast, is literally chooses the middle number of a given set of numbers. And so if I have 11 data points, I'm going to choose what is essentially the sixth one, and that will literally be the middle number. There's 5 below it, there's 5 above it. What is that middle value? The median must always be calculated on a sorted data set, right? If my data set is not in either ascending or descending order, then I can't really find the median. The median won't have any meaning. The mean, by contrast, I don't have to sort things. But why does this matter, and what are the cases in which we use each one? Well, the reason why is because when we look at the frequency of a given value in a data set, we get different pictures. So as an example, this is some of you may be familiar with this curve. This is what is often called a standard distribution, or the quote-unquote normal curve, or a bell curve. Some of you, and don't worry about all this other stuff that's labeling it right now, but if you look at this curve, it may remind you of, perhaps you might have been in a class one time where you heard the instructor say, I'm going to grade this on a curve. What are they talking about in that case? Well, what they mean is that there is this assumption that, for example, in a set of exam grades, that most people are going to do the greatest number of scores, right? Most people are going to do about in the middle, right? They're going to get, I don't know, a 70 or an 80 or something like that. And then a very few people are going to get a very high score, and a very few people are going to get a low score. This standard distribution or bell curve is essentially derived from nature. So this is a pattern that statisticians have identified in a lot of populations. So it's something that you see if you look at height distributions, for example. It crops up all the time in the natural world. That's one of the reasons why it's described as standard or quote-unquote normal, is because it's very frequently, it shows up in a lot of places, right? And it has this very nice kind of symmetrical quality where if you look at this line, This center line that's being labeled here is both, in this case, in the case of the standard, in the standard curve, is both the mean and the median. So it's not to say that the mean and the median never coincide. On a standard distribution, that's exactly what they do. And you can always recognize a standard distribution because of this symmetric quality, right? If I look at where the average is, that arithmetic mean, if I put a mirror up to it, it would replicate the curve perfectly. Now, so that's fine. In cases where we have a standard distribution and we identify the distribution or the shape of a data set by counting, right? What we look at is we look at how many times a given value occurs. Now, we can use the average as an accurate measure of central tendency or, typicality, right? If we have this standard distribution. The question is that the kind of distribution that we have? So by contrast, we can talk about, for example, U.S. income distribution. U.S. income distribution is highly asymmetric, okay? So what this is showing by $10,000 buckets, the income distribution in the United States. So what you can see is that there are over 30 million people, looks like close to, really the x-axis should go higher, but it looks like there are well over 30 million people who make under $10,000 a year as of, I believe, 2015 or 2016, right? And then we see over 20 million who make between 10 and 20,000, et cetera, right? So obviously there's a lot of arguments about income, and as we mentioned in class, there was a lot of backlash about the way that the term average was being used in the description of the recent tax plan, because the question of average versus median and the way that the word average is used to confer typicality is not necessarily accurate in this case. So when we have a skewed distribution like this, what you would find if you were to add up all of the values that are here, and again, what this is showing is the frequency, right? So how many times there is a person who makes between $10,000 and $20,000 a year. And again, it looks like it's well over 30 million times if you were to look at the income of every person in the United States. And then, it gets lower and lower and lower as we go up. And then this, I should point out that this is not a uniform x-axis. So over here, what we're seeing is we're basically seeing everyone who makes over $200,000 a year lumped into one bar, which is why it has that kind of bump in the end. If we were to stretch this out and literally account for every person and their actual income, this would be miles long because there are not many people who make millions or hundreds of millions or billions of dollars a year, but there are some, right? And so the problem is that the mean, that arithmetic mean, okay, is very, very susceptible to what we call outliers. So outliers are numbers like the person who makes $3.5 billion a year. Those are numbers that are way outside the pattern of most of the data, right? So the vast majority of our data we can see even here, even without breaking this out, we know that the vast majority of our data points fall under the $200,000 mark. And so the problem with using the arithmetic mean or the average in this case to describe the middle of this data set is that the mean is highly affected by outliers, right? So that one person who makes $3.5 billion will drag the center point, the apparent center point, really the mean value, will drag it up. And in the sense that we are looking at these as measures of central tendency, right? Again, thinking about typicality, that's really misleading, right? So anytime we have a skewed distribution, we always want to be looking for the median value. Now, the median value is, again, quite simple to calculate in a given data set, because all we need to know is how many individual readings do we have, and if we line all of the readings up, so in this case, we would have 35-ish million readings that were somewhere between 0 and 10,000. We would have another 23-ish that were between 10 and 20,000. And if we ordered that entire data set from 0 to whatever it is, 3.5 billion, and then we literally pick the middle row, and we see what is the income value there, that is going to be our median income. And in this case, where we have a skewed distribution, that median number is the appropriate measure of central tendency. That is what we really mean by kind of the typical or middle value. So what we're going to look at today is how do we find the mean and the median. We've discussed it verbally. I'll just show you very quickly how to do this in Microsoft Excel. And then the other things that give us kind of an understanding of the more general, the broader shape of the data are two other measures. One is called the quartiles, and the other is the standard distribution. So standard distribution goes with normal, these sort of quote unquote normal curve or bell curve data sets. That is a measure of how far something is from that from the mean. And then we have something called quartiles, and quartiles are basically just things that tell us how far a given data point is from the median. So all of these things are ways of describing where is basically the middle point, the appropriate middle point or middle value of this data set, and then how far having something like the quartile or the standard deviation lets us understand how far another data point is from that, right? And all of this is in service of understanding how unusual is data point X, right? So that if somebody comes to me and says, well, I make, or so-and-so makes, $250,000 a year, we can see pretty quickly, we would be able to do analysis and say, well, that is in the, we know that the median is the appropriate measure because we're dealing with an asymmetric data set or a quote-unquote skewed data set. If we look at the quartile or how far it is, there's actually a few measures which you're seeing indicated here. So there's Q1, which is sort of the bottom 25%. There's Q2, which is actually the median itself. Q3, which is the sort of third quarter from the bottom, if you will. And then there are the values above that. And so if I were to calculate what the median how far a given value is from the median. In that case, I can describe it in terms of its quartile, its distance from the median, and understand how extreme that value is, right? And so what we're trying to understand is, does a particular data point fall in the general pattern of the data that we are seeing, or is it an unusual or somewhat extreme value? And that's always kind of our starting point, because that's what we want to know is like, is this unusual or is this very typical? As journalists, very often that's one of the things that we look at to say, is this something that we want to pursue further or research more or report more? Is this something that is unexpected, atypical, or by contrast, a statistic or a data point itself that might seem surprising might turn out to be actually very typical. And then in that case, the story might be how surprisingly typical this thing is. So that's just to sort of give you a sense of it. For our actual data set, and we'll take a break in a moment before we kind of get going here, a lot of you expressed interest in immigration statistics. So if the Department of Homeland Security is now the office that keeps track of immigration statistics. This became true sort of in like 2006, 2007. And what you see is there's a yearbook for every year. And so I did some poking around and found some data tables. And in particular, we're going to look at data table number 35, a subset of table 35, which uses the term alien, to talk about how many people have been apprehended in various jurisdictions in the United States. Now, this only contains 10 years worth of data. So what I have done for our purposes is I've merged together two data sets, the yearbook from 2016 and the same table from the yearbook in 2007, so that we have about 2 decades worth of data to look at. And what we'll do is we'll use that as a way to practice calculating these mean, median, quartiles, standard deviations, and kind of understand what this might look like with an actual data set. So I will be back in a minute and we will get started with that data.